Hi, thanks for joining me in this discussion on ground de-icing. We'll start this discussion on ground de-icing by first talking about the health effects of de-icing solution. After that, we'll talk about de-icing checks, cold soak tanks, and then holdover times. When turbine-engined airplanes are de-iced, usually they shut down the engines. And the reason for that is because any de-icing solution that enters the turbine or the compressor will vaporize, and as a result, that vapor is brought into the cabin of the aircraft. Glycols that are vaporized are hazardous to humans. They can cause eye irritation as well as nose and throat irritation, and also can cause headaches, nausea, vomiting, and dizziness. Also, de-icing solution can cause skin irritation if it is on exposed flesh. And then finally, if for some reason you ingested glycol, 3 to 4 ounces is lethal. Our next item of discussion is de-icing checks. There are 2 de-icing checks that are performed on aircraft, the post de-icing check and also the pre-takeoff check. As the name implies, the post de-icing check is done immediately after the aircraft is de-iced. The post de-icing check can be performed by the flight crew or properly trained ground personnel. The ground personnel will provide the flight crew with information about the post de-icing check, including the solution strength that was used, the time that the de-icing was done, and the time that it was started. Typically, the aircraft manufacturer has a checklist of items that need to be checked after de-icing. Here is an example of the items that must be checked after de-icing on a Boeing 757. You can see that the checklist is very specific. As the name implies, the pre-takeoff check is done right before the aircraft departs. Typically, it is done by either the flight crew or properly trained ground crew, but usually it's done by the flight crew. It is a visual inspection of the wings and other items that can be seen from the cabin or the cockpit. Perhaps maybe you've been on a flight where the flight crew walked down the cabin looking out the windows at the wings to see if the wings had iced over already after the de-icing. The problem with this is that the windows will distort the view out on the wings and other items, so it may not be very easy to see the formation of ice on these items. And as we mentioned already in other videos, you need to check the items that were first de-iced because those items have had the longest time for ice to form. The next item that we'll discuss is cold soaked tanks. Tanks refers to the fuel tanks that are at a very cold temperature as a result of one of 2 things. Either the aircraft was at high altitude, and of course, fluids have a much higher specific heat, so it takes longer for them to acclimate to the new temperature. So if the aircraft was at a high altitude, let's say temperature of minus 40 degrees Celsius, when it lands, the fuel in the tanks may still be minus 40 degrees Celsius. The other cause of cold soaked tanks is if the aircraft is refueled with cold fuel. For example, if you have tanks that are very cold and you put that fuel into the aircraft, then of course the wing will be cold as a result of that cold fuel. So the fuel tanks that are in proximity to the wing, that are in the wing itself, will cool the wing, the surfaces of the wing, both the top and the bottom. And as a result, if the air is more humid, then you will have the formation of ice going straight from either the vapor to ice phase, or it could even have condensation that freezes at a time later that produces ice on the wings. So this is the problem with cold soaked tanks. You get the formation of ice on wings in environments that may be warmer than 0 degrees Celsius, 32 degrees Fahrenheit, but you have high humidity in the air, that results in ice forming on the top and the bottom of the wings. The solution to the problem of cold-soaked tanks is to either de-ice the airplane with type 1 solution or to fill the fuel tanks with warm fuel to raise the temperature of the fuel itself. The last item that we'll discuss in this video is holdover times. Time refers to the time that de-icing or anti-icing solutions are effective. In other words, the time at which ice will form on the wings after the application of either de-icing or anti-icing solutions. There are many factors that are involved in determining the holdover time, and there are tables that estimate the time that the ice will form after the application of de-icing or anti-icing solutions. Holdover time tables are created by the FAA and also the manufacturers of the de-icing and anti-icing solutions. Pilots need to be familiar with these tables and consult these before departing and also after de-icing an aircraft. You can see that there are several columns. The first column has outside air temperature. That is probably the most important factor. The next one, going over to the second column, is the concentration of the de-icing solution in a split of fluid versus water. For example, 100%/0 means that it's 100% solution and 0% water. Notice at the very top of this table, it says that this is a generic holdover time for type 4 fluids, so this is an anti-icing fluid. And then the columns after that give you times for which at a particular temperature and a particular weather phenomena you can expect the de-icing solution, or in this case anti-icing solution, to fail. Fail meaning for the solution to turn to ice. For example, the third column shows freezing fog or ice crystals at a temperature of -3 and above, -3 Celsius. The first line shows that if there is freezing fog or ice crystals, the de-icing solution is good for anywhere from between 1 hour and 15 minutes to 2 hours and 40 minutes. As the type of precipitation becomes more hazardous, for example, freezing drizzle or freezing rain, you can see that the de-icing time or the holdover time is reduced dramatically. For example, if we go all the way to the right side for light freezing rain at a temperature of -3 degrees Celsius, the very first row, you can see that for light freezing rain, type 4 solutions will fail between 25 minutes to 40 minutes of time on the ground. And then rain or cold-soaked wings, you can see the time is even shorter. As you go towards the bottom of the table, the temperatures are much colder, and as a result, you have much shorter holdover times. There are a lot of factors that go into determining holdover times, and we'll look at that on the next slide. Here are some of the factors that go into determining holdover time. Some of these can be estimated and are included in the tables. Others are not, and you can just have to estimate. Here's examples. So aircraft component inclination, angle, contour, and surface roughness cannot be estimated. But in other words, if the wing surface is at a great inclination, the solution will slide off of the wing. Ambient temperature, of course, is included in the tables. Aircraft surface skin temperature, a little bit different than ambient air temperature, and that's a little bit more difficult to estimate. Fluid point depressant or FPD fluid application procedure. How do you apply it onto a wing? That's not included in the holdover tables. FPD aqueous solution strength, that is included in the holdover tables. For example, 100% solution /0% water or 50% solution /50% water. FPD fluid film thickness is not included, nor is the FPD fluid temperature. As you know, de-icing solutions are typically heated before they're applied to an aircraft. Here are other factors that affect holdover times. FPD fluid type, we saw that, is included in the tables. Operation in close proximity to other aircraft, equipment, and structures is not included. For example, buildings may give off heat or infrared radiation, resulting in warmer aircraft skin temperatures. Another item, operations on slush, snow slush or wet ramps, taxiways, and runways. Slush is being thrown up on the wing or aircraft surfaces. It may refreeze a little bit quicker. Precipitation type and rate, remember that that is included in the holdover tables. However, the amount of precipitation as you get greater snowfall or freezing rain rates, that will dilute the solution and make it weaker and perhaps maybe fail at an earlier time. Another item, presence of FPD fluid, that's included in the tables, and then also radiational cooling, meaning that as the sun sets, the aircraft structure will start to cool because it is no longer absorbing solar radiation. That was a lot of information on ground de-icing. I hope that gives you additional insight on how operations occur at airports where there is de-icing and anti-icing operations in progress.